For those of you who weren't here, I have been teaching courses related to risk management and specifically liquefied gases and process safety related for a number of years, and this is all about preventing loss of containment. And that's the theme is how do you design systems, maintain them so they will operate safely and prevent loss of containment. And flammable gases are a big issue in terms of loss of containment. And in the title there, I've listed a number of hydrocarbon gases, methane, propane, butane. I'm going to talk a little bit about all of those, but mainly about propane. In the abstract that I submitted, I said I was going to talk about hydrogen. For those of you who came to hear about hydrogen, I am sorry, I'm not going to do it. There is not enough time. When I got into it and decided, I didn't want to cut out a number of the examples on propane and the whole issue of hydrocarbon gases. So we'll do hydrogen next year if I teach the course. So those of you who want to leave now, I'm sorry if you came just for hydrogen. So we're going to be having 4 sessions today. In the afternoon, I'm going to talk about chlorine and oxygen, mainly about chlorine, and then the last session will focus on ammonia. And again, I've got so much on ammonia, I'm not going to go into much of any detail on SO2 this time. Let's talk about what is a flammable gas. First, we talked about what gases are, gases and compressed gases at the last session. And a flammable gas is a gas that forms a flammable mixture with air at a concentration of 13% of volume or less. So by that definition, we have 3 gases that we're going to talk about in great detail during the day today: chlorine, propane, and ammonia. Ammonia will burn. But is it a flammable gas? What was your answer? In Canada. Yeah, okay. What was your answer?
I've seen MSDSs that would indicate that it should be regulated as a flammable gas. Because of the
Yeah. It's got a wide range. The second definition: a gas at ambient temperature and pressure forms a range of flammable mixtures with air wider than 12% by volume. And it is wider, but it's less than. It's 13% volume. It's 15 to 30 roughly. So it could be, depending on the definition, it could fall into either. But there are a number of other reasons why there are exemptions for ammonia related to minimum ignition energy, and we'll talk about those characteristics in terms of gases when we get into ammonia. So in flammable gases, I'm going to focus on the lower molecular weight hydrocarbon gases. Now, I'm going to specifically talk a lot about natural gas liquids or petroleum refinery gases, which are often known as liquefied petroleum gases, LPG. LPG comes from 2 sources. If you look on the diagram here, we see we've got natural gas and we've got refineries. And natural gas, when it's produced, when you have wet natural gas, it has higher hydrocarbons other than methane. It has ethane, it has propane, it has butane, pentane, etc. In refineries, you'll also get a variety of hydrocarbon gases. Now, there's this triangle, this ternary diagram with the hydrocarbon and then nitrogen and air showing different percentages. On these diagrams, there are only 2 numbers that you typically use, and then there's a third at the nose of this little area here. These diagrams for different fuels are determined experimentally, and they're done in a calorimetry bomb. and you get a combustible zone like this, and this is typically shown as the upper flammable limit and the lower flammable limit, those 2 points, and this one here is the minimum oxygen concentration. And so that's where these numbers come from, is from the experimental data that's generated in this bomb, and this has been done for decades. So all of this information is typically in the literature. What gets more difficult is when you have different hydrocarbon vapor mixtures. And again, the Bureau of Mines has published back in the 1960s and 70s are also mixture data. But it gets a little more complex. But generally, it's pretty easy if you've got a relatively pure gas. And here are the lower and upper flammability limits for a range of gases. Propane's 2 to 10%, methane's 5 to 15. If you look at down here is higher hydrocarbon like pentane's 1.5 to 9. So that's where these numbers come from. Now, as all of you know, we're in a real nice situation in terms of natural gas supply in the United States. We've had an increasing supply because of the hydraulic fracking, which means we're also going to have an increased supply of natural gas liquids. So there's going to be more propane around. Now, what has been the trend in terms of propane use and growth in the U.S.? This diagram shows a lot of the natural gas pipelines. There's a lot of the U.S. served by natural gas pipelines. And so that has actually cut into the use of propane somewhat, but we're also still using a lot of propane in various other end-use markets. By 2035, we should see a significant increase in the total production of natural gas in the U.S., and with much of that coming from hydraulic fracturing. Now, in terms of supply sources and demand, where do these components, these flammable gases come from, and what are they used for? Well, in terms of ethane, 90% comes from natural gas and 10% from refineries. 100% steam crackers for ethylene is what its demand is. That's what ethane is used for. Now, when we talked about, and let me go forward a little bit, boiling point and temperatures and pressures. So ethane, why is ethane used as a petrochemical feedstock and not as a fuel, and why isn't it transported a lot? Well, the answer is very simple when you look at the physical properties. When you look at the vapor pressure of the gas at 100 degrees Fahrenheit, let's start at 70. At 70 degrees Fahrenheit, it's 560 psi. Ethylene, I'll skip over since I didn't put the number in there. I don't know why I left that out. Propane's 125 and propylene's 150. You can easily store propane as a liquefied gas at room temperature at 125 to 150 degrees, 150 psig in a pressure vessel. It's much more expensive to store ethane. So from the standpoint of looking at physical properties, that's why propane is such a valuable fuel in terms of its ability to ship it as a liquefied gas at relatively low pressures. Methane is even much higher in terms of pressure. To be able to ship methane, and the critical temperature is very low for methane, as I talked about in the first session. So the methane has to be liquefied as a cryogenic fluid, which makes it much more expensive. So propane is the ideal gas. Now, butane, which I didn't put on that, I don't remember if I've got on the next slide. Whoops. I didn't put butane. So butane has an even higher boiling point and a lower vapor pressure, and it's not as good a fuel for use for industrial heating and for home use heating. And the reason for that is what? its vapor pressure isn't high enough. If you're in Minnesota or up in the Sierras in the middle of the winter, and you've got if you've got a tank of butane outside, it's not going to have enough vapor pressure to pressurize the lines to get it into your burner. So that's why butane is not as widely used. And propane is not, for fuel use, is not pure propane. It has a certain amount of butane and some propylene in it and some butadiene and so forth, some trace components. So it's not pure, but it's close to what this number is here in terms of vapor pressure. So even on a hot day, 100 degrees F, propane cylinders 190 psi. Propane cylinders are typically rated at what pressure? 250 to 300 psi. Now, in terms of some of these others, when you get down to butane, it's about half and half coming from natural gas liquids or from refineries. And I'm telling you this because, and I didn't ask the question, I did the first time, how many of you work for a state agency or for a CUPA as a regulator? A lot of you. How many of you work for an owner-operator that might have some of these types of gases? Okay, a number of you. So those of you who are in the regulatory business to regulate folks, if you're in this area and near a refinery, you might see a butane sphere. But if you're not near a refinery, you're probably not going to see a butane sphere, but a lot of you may see propane cylinders and propane tanks all the way up to 50 or 60,000 gallons. Historical perspective on propane sources and use in the U.S. Where is propane used? About 45% to 50% has typically been used in commercial and residential applications. 5, 6, 7% used on farms. I'm going to talk about some of those. A lot of it's used for petrochemical applications, very little for transportation fuels, and a little bit for industrial use in terms of a process use. There are millions of propane fuel users out there, so one of the reasons that I focus on this is because of the high tonnage and the fact that there's a lot of propane out there in terms of individual users in commercial, industrial, residential, and there are a lot of distribution centers for propane and propane suppliers who deliver in tank trucks and bobtails. And they'll also deliver cylinders. I'm going to talk, and we're going to give some examples. I'm going to give examples at all points in the distribution chain, in the supply chain. 90% of propane has historically been produced in the U.S. with the remainder imported from primarily Canada, but also from Mexico. We are going to become probably a net exporter. We'll still probably import some because of the supply-demand balance and along the border and with certain contracts. We're probably not going to completely eliminate the import of natural gas liquids, but we're probably going to become a net exporter because we're going to be generating more, but we may also be using a lot more as chemical feedstocks. As I mentioned, outside North America, there's much higher butane if you're in a lower part of the world in terms of closer to the equator, then the liquefied petroleum gas that's shipped around may have a higher butane content because you don't have this concern about during the winter being able to supply burners at adequate pressure. As I mentioned early on, the big three, and propane, of the three we're going to talk about, is the largest in terms of consumption worldwide. Over 250 million tons per year, a lot of usage. Propane vapor pressure versus temperature. As I mentioned, and you'll have this in the slides when I post them, the critical temperature of propane is above normal atmospheric temperatures you will experience, so it can be present as a liquefied gas. It can also be present as a compressed gas, but at the pressures and normal room temperature and the pressures it's stored at, it's typically going to be just like this. And when you know the pressure in this vessel, if you have a pressure gauge on a storage tank, you will know the temperature if it's well mixed. Vice versa, if the pressure gauge is faulty and you know the ambient temperature and you think that vessel is about at that temperature, in other words, it hasn't been used in terms of supplying a lot of material. I don't know what I just pulled there, but you will know the pressure by knowing the temperature just by having a vapor pressure temperature curve, and that can be very important if you have a faulty gauge and need to know what the approximate pressure in the vessel is. Now, we're going to talk about accidents that occur at various points in the supply chain. And we're going to talk about transport issues and how liquefied liquefied petroleum gas, or propane primarily, is transported, and it's done in a variety of ways. How it's stored in various points during the supply chain. How it's used in terms of filling cylinders, different types of transport vessels, and then the different types of uses. And I'm going to talk about accidents. I'm going to talk about 12 different accidents that have occurred, some of them involving hundreds of fatalities with propane. Now, in terms of the transport, propane is transported by ocean-going vessels, by barges, by rail cars, by very large transport truck trailers, by what are called bobtails, and also put into smaller cylinders that are transported in individual vehicles or on trucks with multiple cylinder loads. In terms of pipeline transport, we have a number of natural gas liquefied petroleum gas pipelines in the U.S., none in California at this time. And one of the things about the demand for propane is the demand fluctuates, with 45% of the demand being related to commercial and residential. A lot of that residential demand is for home heating, cooking, and heating. And so the demand goes up and down, as does the demand for natural gas, which is the source of the natural gas liquids. And so what we have to have in the supply chain are places to store natural gas and natural gas liquids. And those are typically stored in underground reservoirs. And I'll get to that in a moment, because I forgot that I had this slide in between. In terms of transport with large vessels, another thing that's done, because of this fluctuating demand and wanting to be able to utilize the transport vehicles on a nearly full-time basis, these large transport vessels, like these tanker vessels, transport both liquefied natural gas, or LPG, and they also transport anhydrous ammonia. And the same is true for transport on the railroads. You'll see transport of liquefied petroleum gas and ammonia in the same transport vessels. Now, in terms of the actual production of natural gas liquids, not all natural gas has high natural gas liquids. The more profitable wells do have natural gas liquids. These natural gas liquids, including the higher condensate, when you get up to the C5, like the pentane and hexane, which is essentially can go right into gasoline, is high value. So a natural gas producer is very happy when they get what's called a wet gas well, because you get a lot of ethane, propane, butane, and pentane in that gas, in differing proportions and different amounts in terms of total amount in the gas. And those gases are removed in what are called fractionating columns at natural gas liquids processing plants that are located in various parts of the world and around the U.S. as well. And as we start to produce more natural gas across the U.S. from fracking, we're going to see more and more of these natural gas liquids plants at various locations. You remove the natural gas liquids, and you also remove the acid gases and inert gases. You remove CO2, nitrogen, as well as, in some cases, mercury, as well as H2S from the natural gas before it goes into the natural gas pipeline. The regulation of the pipelines is done by the U.S. Department of Transportation and as well as the U.S. Coast Guard for various pipeline and vessel transport and near shore and offloading, where you have a pipeline that is offloading onto a vessel. So the Koopas probably don't get involved, other than you should know about these situations in terms of the different types of risk exposures from transport. One of the interesting things, I talked in the first session about a risk-based approach. The DOT has taken a risk-based approach for implementing the Pipeline Inspection, Protection, Enforcement, and Safety Act. And this is a theme that I think you're going to see much more of throughout all levels of government in the future, is taking a more risk-based approach rather than having very specific threshold levels. It's going to be based more on looking at the actual risk exposures in terms of determining the control levels. Now, in terms of these caverns for storage of hydrocarbon gases, if you look here, some are in caverns, some are in depleted oil fields or depleted oil and gas fields, where both natural gas or liquefied petroleum gas are stored so that you can meet this fluctuating demand for either of these types of fuels. And so this figure just shows some of the areas around the U.S. where there's some major locations for such storage reservoirs. Now, during this session, I'm going to talk about 12, actually I've got more than 12, and I'm going to talk about 12 different incidents, some of them pipeline failures, some of them railway tank cars, and I'm going to give examples from fairly long ago, back in the 60s and 70s, and talk about what went wrong there, talk about some of the standards that were changed in terms of design and how that has altered the landscape in terms of the risk exposure for transportation accidents. I'm going to talk about some very large storage facilities where at the end of pipelines, either coming from natural gas liquids facilities or from refineries, where very large quantities of propane are stored, in some of the very serious accidents that have happened in the past. I'm going to talk about refinery accidents where propane is not only used as a feedstock, where you dehydrogenate propane to make propylene for polypropylene, but also where you can use propane as a solvent, for example, in solvent deasphalting. Talk about a very serious incident that happened there. And then I'm going to talk about end users and convenience stores and on-farm use and some things that have gone wrong that have led to fatalities. Now, in terms of the natural gas liquids pipelines, there aren't a lot of them, but there are some. And at the terminal end of some of these pipelines, for example, one of the largest ones, which is right outside of Houston, there's a large natural gas storage reservoir. And in February of 2011, at one of the natural gas liquids facilities there, they had, during a maintenance operation, loss of containment event, and this was the result. A very large fireball that you see here. They had a vapor cloud explosion, and then a fire resulted. And these can result in a number of different kinds of fires, and I'll be talking about those, how those fires are classified. Here's a pipeline fire that occurred in May of 2001. I don't know the history on this one in terms of the reason for the propane line break. There were no serious injuries or fatalities here, but as you can see, with a propane fire, when you have, it's being pumped at high pressure, it's a liquid. When that liquid comes out and flashes out, you see all that black smoke and you see that fireball. That's indicative of a certain kind of situation where there is so much fuel coming out of there that it's not completely burning. So you're getting some vapor burning, but you're also getting a lot of droplets, and you're getting fireballs. So you have what's called a fireball, which is burning from the outside of a liquid mass in. And you're also getting a lot of black smoke soot formation because you don't have complete combustion. And we're going to talk about the difference between a fireball and a vapor cloud explosion. Because a confined vapor cloud explosion is extremely serious. This is serious too. Just the radiant heat off of that can kill somebody too, very seriously burn them. But we'll talk about some of the differences. And one of the reasons I'm mentioning this, and you may not get involved in this, but one of the things when we do a process safety evaluation for handling flammable gases, as a chemical engineer, what we get involved with are consequence analysis, where we have to look at what can happen when we have that release from that line. Is it going to be a vapor release only? Are we going to get a vapor cloud explosion perhaps? Are we going to get a torch fire or a jet fire, which has also serious consequences? Very difficult to put out a torch fire. Or are we going to get a situation where we're going to get a BLEVE, which we will have large amounts of liquid, when this vessel fails, thrown up into the air, and we're going to not have a vapor cloud explosion typically, we're going to have a fireball where we've got this liquid burning from the outside of the droplets in. It's a much different scenario situation. So all of these get looked at in determining what kind of risk mitigation measures to put in place. Yes, ma'am? No. I don't think that's what happened here. I'll talk about what a BLEVE is. I mean, this theoretically, if the pipeline had been shut down and it had heated up and there was mechanical damage on the pipeline, it could have BLEVE'd. But I don't think that's what happened here. So I won't say categorically that's not what happened, because I didn't go and look to see if there was a National Transportation Safety Board report. I did actually look, but I didn't find it. So I don't know if there was one on this event. But I doubt if this was a BLEVE. So one of the famous BLEVEs that led to a lot of soul searching about how we design railway tank cars was an accident that happened in 1973 at Kingman, Arizona. This was a BLEVE of a propane rail car. Killed 11 firefighters and a gas company worker. And the sad thing about this is we keep having to relearn these lessons about BLEVEs of liquefied gas tanks. And what happened after this incident, we had a lot of different changes. There were over 100 more people injured. You can see after a BLEVE, you typically get a big fireball. But a BLEVE does not have to be associated only with flammable gases and liquefied flammable gases. Liquefied gases stored under pressure at significantly above their boiling point in temperature will BLEVE under the right conditions. And so we'll talk about that and going through some examples. So in response to incidents like what happened at Kingman, railway tank cars have been redesigned. Single-wall steel rail tank cars are not used anymore. They've been replaced with double-walled tanks protected with an inner layer of insulation that increases, it doesn't prevent BLEVEs, but it increases the time you have to react before a BLEVE will occur. But it doesn't mean it won't happen. And there are numerous other changes. Now, what does it require for a BLEVE to occur? And a BLEVE is defined as a boiling liquid expanding vapor explosion. It's actually a deflagration. But whether it's a deflagration or explosion, if you're 100 or 200 feet away, it doesn't matter. You might be killed by either shrapnel from the vessel that is blowing apart or from the fire and flame, if it's a flammable gas. So the conditions are the pressurized container must contain a liquid. Got to have a liquid. The liquid must be at a temperature well above its boiling point at atmospheric pressure, and the container has to be at an internal pressure that exceeds the strength of the container. Now, does that mean that it has to be above, let's say the container is rated at 300 pounds gauge pressure? Does it mean that the pressure in that vessel has to be above the rated pressure? This is a trick question. No, it does not. Theoretically, the answer would be yes. But if that vessel is damaged, mechanical damage, if it's a tank trailer, if it's a trailer, that tank trailer that has gone off an overpass and it's been damaged by a long scrape along its side, that vessel wall now has been compromised and no longer has the rating it did when it was past the inspection. It was hydro-tested. If it went through a derailment and it has also had damage from sliding along the ground and hitting a rock and having a large dent put in it, it may have been compromised in terms of its strength. So that vessel might BLEVE at less than its maximum allowable working pressure. So, for example, if you write in your jurisdiction, if a propane tank has overturned and has slid along the ground and had significant damage on its side, and they're ready to rewrite that tank, and it does it during the night, low temperature, a lot of the insulation is damaged. During the day, what happens? Heats up, pressure increases, vapor pressure temperature curve. Someone takes the crane and starts to rewrite that vessel, it can BLEVE. And this kind of thing has happened. And so that's one of the reasons that you call the American Chemistry Council and the Chlorine Council authorized contractors and the various groups that I'm going to talk about to help deal with those situations. What causes BLEVEs? You can overfill a vessel with an inoperable or undersized pressure relief device. So you can just physically put too much liquid and it can cause a BLEVE. You can have the mechanical damage I talked about. You can have corrosion that causes structural weakness. One of the classics is the next one. You've got a whole list, a line of tank cars in a train. One tank car's got propane in it. The next one, 2 cars up, has got chlorine. The next one's got ammonia, 2 or 3 cars up. You have a derailment. They're all suddenly in a big heap, 4 or 5 cars strewn different directions. The propane tank car has a breach of its wall. You got an ignition source and you got a jet fire impinging on the wall of the chlorine tank. Perfect scenario for a BLEVE. The vapor pressure starts going up in the chlorine tank. The pressure relief valve on the tank car relieves. Are we home free because it's relieved? Are we going to have a BLEVE? Because the pressure relief valve releases on a pressure vessel does not mean that it will not BLEVE. If you have a torch fire, for example, the amount of heat going, the amount of energy you're putting in that in terms of heat energy is going to be so much that you're probably still going to reach a BLEVE even if you've got multiple relief valves on the system. That's what my warning is down here. Don't assume that a venting pressure relief device, whether it's a rupture disc or pressure relief valve, will prevent a BLEVE on a liquefied gas tank. It can still happen, and it has. Now, there's some examples. If you read a paper, and I would advise you to go to this, it's online. I wrote the website address here by Peterson on BLEVE facts, risk factors, and fallacies in fire engineering in April 2002. And he gives some examples, and these are not in the 10 or 12 that I listed, of specific examples. One was with a scrape on the bottom of a 33,000 gallon anhydrous ammonia rail car that BLEVE'd when it was righted from mechanical damage. Another one at Waverly, Tennessee, which is a butane rail car, BLEVE'd 2 days after a derailment because it received mechanical damage. And probably the temperature went up. And this, again, this was in the 70s and was probably a vessel that didn't meet current standards in terms of insulation. And then there's another example with mechanical breach occurred, causing it to fail violently. How far can the debris go from a BLEVE incident? A lot of firefighters, and if you're in the fire service or if you're in a Cooper that's called out to an emergency situation with a liquefied gas, the shrapnel can go thousands of feet. It's a very serious situation. Now let's talk about types of fires, pool fires. If you have large amounts of a liquefied material flowing into an enclosure, a secondary containment area, or a recessed area, for example, under a propane tank, you can have a burning pool fire. It's not necessarily going to happen very often. You can also get a flash fire where you have, and I'm going to show some examples in some videos, where you have material released, it vaporizes, and the vapor cloud moves along until it finds an ignition source. When it finds that ignition source, it is going to flash back to the leak source, and if that's under pressure, you may end up with a jet fire or torch fire. If the tank BLEVEs and you have a mixture of vapor and liquid, that's when you get these large fireballs. They're typically related to a mixture of both liquid and gases that are burning. Now, when you have flammable vapor explosion, vapor spaces, if you are in an area where you have lack of confinement, you're not getting a vapor cloud confined between two buildings in short distances between pieces of equipment, you may not develop high overpressure, but you might if you have enough confinement. And certainly in a closed room, or where you may have a gas line or propane going through a structure and you have a leak, then you have the possibility for an explosion because you've got a confined situation where you're going to get rapid burning and rapid pressure buildup. Outside, you're going to more likely get a flash fire. Inside, you're going to get a vapor cloud explosion. You can also have physical explosion from overpressurizing. Now, another question. If I have a liquid reaction vessel, and there's a very famous case study example that we use in this course I was telling you about on risk-based process safety, can you have a BLEVE with water in a vessel? Absolutely. Gramercy, Louisiana, 1990s, there's a bauxite ore refining operation for alumina ore refining, where it was being digested in vessels at high temperature and pressure, and they ignored a number of safeguards. They ignored the standards, ASME standards. They were operating purposely above the the rating on the pressure vessels. They had a situation with a power outage. The control systems still worked to some extent, but they couldn't control the outlet and the inlet to the vessel for the feed lines, but they could, but the automated control for feeding steam to the unit continued to operate. So they kept building up temperature and pressure, and they had a BLEVE of a water vessel with about 20 to 40% caustic in it. And the structural damage was extreme from the BLEVing of that vessel. So again, remember the definition. If you have a liquefied gas at significantly above its boiling point at atmospheric pressure, what's the boiling point of water at atmospheric pressure? 212 degrees F. They had this vessel at 300 or 3-something degrees F, and it BLEVed when it got above its rated pressure significantly. Now, what was done after the Kingman, Arizona? There were a lot of changes made to how railway tank cars are designed. They've got something called top and bottom shelf couplers now, like thumbs. Before this time, the couplers used to be able to just slide up and down. And why was that? So one car derailed, not all of them derailed. And what would happen then, you might get a situation where you would get one car derailed and you have the other cars, and you'll have the coupler going spearing right into another tank. And so it was decided it's a better practice to keep all the cars together and to have a top and bottom coupler so that you won't be able to uncouple. So what does that mean? You derail more cars. But you're not going to have as likely situation where you're going to have a penetration of one vessel into the other. Tank head shields for puncture resistance, somewhat effective. Depends on where the penetration occurs, where the spearing occurs. And if you have a derailment and you have a car going into if you have a side penetration, if you've only got the head shields on at the head of the tank, that's not going to help on the side, right? So there are some limitations there. The biggest thing is thermal protection. You've got more time to figure out what you're going to do before the tank BLEVEs. But you've got to know what to do and when to back off. And they're designed, thermal protection, to protect the contents in fire situations and prevent any loss of contents except that discharge through high pressure relief valve for 100 minutes in a pool fire and 30 minutes from a torch fire, a jet fire. And again, there's a big difference between a pool fire and a jet fire and proximity to the vessels. And so again, this is when you're responding to situations and when you're looking at scenarios, you've got to make certain that these different kinds of scenarios have been appropriately considered. I think I've already talked about all of those. Whoops. Now, 2011, propane rail tank fire in Northern California in August 2007 at Lincoln, California. What is the good news about this story? The good news about this story is that this tank did not BLEVE and there weren't people killed. This tank had those design features that were not present when the Kingman, Arizona incident happened. It makes a big difference. Was it certain that this tank wasn't going to BLEVE? No. But these safeguards made a big difference, the tank being insulated. Now, when you have a tank releasing through its pressure relief on the top of the tank, and they're all in that protective housing that's up there in the tank, and that's where the liquid withdrawal is, that's where the feed is, and that's where the pressure relief is. It's all there right on the top. And that's one of the ways you can tell a tank car that's carrying liquefied gases versus tank cars that are carrying others. Tank cars that are carrying liquefied gases have no external penetrations on the bottom of the vessel. It's all up there on the top and it's all protected by that enclosure. So that's another thing when you're responding to incidents. And there's a lot of information you can find. I just put an example here. There are a lot of DOT specs on these vessels and placarding. There are also various training courses that are given. And I'm just going to hit the highlights. I've gone to some of these just to see what's given. And this is one that happens to be given for TransCare for shipping high pressure anhydrous ammonia and LPG. And they also give instruction on low pressure vessels and for cryogenic shipments. And go over what is required in terms of response, the different types of ways to respond to leaking valves on the tops of rail cars. Hopefully if it's propane, it won't find an ignition source before you get the leak fixed. Or if it's already started overpressurized, that you're not going to have an ignition source for that venting gas coming out of the top of that pressure relief device. This shows the closed cover showing the pressure relief vent opening that's going to flip open during a venting incident. Now, let's talk about an incident in 2009 that didn't have such a happy outcome as what happened in Lincoln, California, where we had no fatalities and no injuries. June 29, 2009, 14 liquefied petroleum gas cars in a train going through the town of Viareggio in northern Italy. Derailed. One of the tank cars was punctured, hit a signaling stake. The LPG was released. The dense gas cloud of propane formed after the release of the liquid, moved towards the surrounding neighborhoods. Some of the material moved into basements, into the ground floors. What did we talk about propane in terms of gas density? Higher than air. Explosions and fires produced a high number of victims, 31 fatalities, 30 others with serious injuries. Some of them with small children. Their parents took outside, trying to get outside, put them in a car, went back for their other children. Their children were incinerated. Terrible event. A dynamic analysis of the accident showed that it probably took less than 90 seconds for the dense gas cloud of propane to reach the furthest house that eventually exploded. How can you respond to a situation like this? 90 seconds. It's impossible. You've got to prevent loss of containment. Remember I talked about preventive containment and mitigative measures. What can you do in 90 seconds? It's nothing. Virtually nothing can be done to react in that short time frame. So the key is you've got to prevent the loss of containment. So I'm going to show a video and stop talking for a while. and then I'll come back and talk about this incident. What I'm going to talk about is a flash fire and then jet fire that occurred at the McKee refinery, and this is a Chemical Safety Board video in Sunray, Texas, 2007. And this shows a lot of what can go wrong and some of the mitigative measures that weren't adequate.
On February 16, 2007, a massive fire broke out in the propane deasphalting unit at the Valero McKee refinery near the town of Sunray in the Texas Panhandle. 3 workers, including a contractor, suffered serious burns. 11 others received minor injuries. The fire occurred after liquid propane was released from process piping in a deasphalting unit. The rapidly spreading blaze forced the evacuation of the entire refinery.
The CSB investigated because of the serious nature of the accident. The fire shut down the refinery for 2 months, and it operated at reduced capacity for nearly a year. The shutdown contributed to temporary shortfalls in gasoline supplies in some markets.
The fire caused extensive equipment damage. Valero estimated that direct losses exceeded $50 million.
Our investigation found several key factors combined to cause this damaging fire, which in turn led to 2 near misses that could have been catastrophic.
The following animation depicts the sequence of events the CSB determined likely led to the accident. The propane deasphalting unit, or PDA, used high-pressure liquid propane to separate asphalt and gas oil from a heavy petroleum mixture known as pitch. Propane flowed through a control station, up a vertical pipe, and into an extraction tower. When the process was originally designed, propane also flowed through a second control station, mixed with pitch, and entered higher up on the same extraction tower. But in the early 1990s, the process was changed, and the use of this second station was discontinued by closing several valves. This created a dead leg, a section of piping without any flow through it. The CSB later determined that, unknown to operators at the time, a foreign object, a piece of metal, had wedged under the gate of one of the 10-inch valves, preventing the gate from closing fully and leaving a path for liquid to seep past the valve. The propane above the valve contained small amounts of water. Some of the water, which is heavier than propane, sank through the valve and accumulated in the piping elbow below.
The piping dead leg formed by the mixed control station had been left connected for years, apparently without incident. But now, in February 2007, conditions arose that would lead to a pipe failure.
That month, a cold snap dropped temperatures well below freezing for 4 days, reaching a low of 6 degrees Fahrenheit on February 15th. Water in the piping likely froze, expanded, and cracked the piping elbow. For a time, the ice itself prevented propane from escaping, until around 9 a.m. on February 16th, when the temperature climbed above the freezing mark and the ice began to thaw. At 2:09 p.m., the melting ice gave way. High-pressure liquid propane from the deasphalting unit began to escape through the small opening in the leaking valve and out the cracked elbow. The CSB estimated the initial flow rate of propane at 4,500 pounds per minute. A large flammable vapor cloud rapidly formed. The wind blew the propane cloud toward a boiler house. Moments later, the cloud ignited. Flames flashed back to the cracked piping elbow, creating a high-pressure jet fire. The fire rapidly damaged nearby pipes, causing a second jet fire aimed at a non-fireproofed steel support structure under a pipe bridge 77 feet away. Within minutes, it collapsed under the intense heat. This broke open numerous lines filled with flammable materials flowing from other parts of the refinery. The growing blaze threw massive fireballs and thick black smoke into the air. A surveillance camera captured the spreading fire. The alarm was activated at 2:10 p.m., a minute after workers heard what they described as a popping sound from the first propane release. The refinery's emergency response team attempted to turn on stationary firewater monitors, but shifting high winds hampered their efforts. 15 minutes after the fire erupted, managers ordered the total evacuation of the refinery. This decision may have saved lives, because the large extractors full of propane might have failed catastrophically, or the fire could have affected nearby units that contained other hazardous materials.
The CSB investigation identified shortcomings in process safety management at the refinery and disclosed gaps in industry guidance on safety equipment and practices. The CSB issued recommendations to the American Petroleum Institute, the company, to the McKee Refinery, and to the United Steelworkers and its local.
This accident began in a section of liquid propane piping that hadn't been used for up to 15 years. At the time when its use was
all of these videos from the Chemical Safety Board you can download off of www.csb.gov. So I'm just going to go through a couple of lessons learned from this example and talk about some of the issues there. One of the problems that was not identified with the way the system was designed, they didn't evaluate the hazards associated with the shutdown of a portion of the piping, this dead leg, and so they didn't really look at what could happen. So they didn't even have as one of the scenarios that they could have this ice, they could have accumulation of liquids in this area and then have the, I see my microphone's not, is that better? They could not operate the system safely because of the potential to have a collection of liquid, possibly water, in this dead leg. They did not comply with Valero's mandatory internal emergency isolation valve standard. One of the problems that was not described yet in the video at the point when I shut it off was that they couldn't get to the emergency isolation valves to shut down the flow of fuel. It is virtually impossible to put out a jet fire. You either have to blow it out with an explosive charge, or you have to cut off its fuel source. And in this situation, they also had, it was exacerbated by the fact that they had these other combustible liquids coming out in the failed pipe rack, and so they had a pool fire. And they also couldn't get to valves that would actuate cooling systems and deluge valves for those large butane spheres that were off in the distance. And those could have BLEVE'd in a fire situation if the wind had changed direction. So another factor in this design, they did not have fire protection up to a certain level on all of the pipe racks. And this was a deficiency in the standards. They met standards, but the standards were not adequate in terms of the risk exposure. So this is an example. Remember I said you need to look at the hazards you're dealing with and the specific risk exposures. And for those of you who are in the CUPAs, hopefully you can get to your regulated community to be doing that. In this situation, they didn't look at the scenario of a jet fire and the possibility that that jet fire would be large enough to impinge on non-fire protected structural steel. And so they had not put fireproofing on the structural steel all along that pipe rack because they didn't look at the scenario of a potential jet fire from a propane deasphalting unit, which would have been a logical scenario to look at, that you would have a jet fire. So this is a situation where standards were not adequate. So being in compliance with standards does not necessarily mean you have a tolerable risk situation. Now these are the four 10,000 barrel, 420,000 gallon each spherical tanks were nearby. And this is the damage on one of them. And under slightly different circumstances, this could have been a BLEVE, because that is near the top of the tank. And where are tanks most susceptible to BLEVEs? When above the liquid level. When you have a pool fire that's below the liquid level, it doesn't mean the vessel won't BLEVE, but it will BLEVE a lot less rapidly. If you have a jet fire impinging, or if you have a jet fire with radiant heat radiating onto the top surface, you weaken the top surface. And once it gets to 1,000 degrees F, what's it do to the strength? 50% less. And it rapidly drops off from there. And what happened at the McKee refinery in Delray, Texas? Most of you are too young. I was too young to remember it. There was a BLEVE. 1956, same refinery. 19 firefighters died when a pentane and hexane vessel was BLEVE'd. So it's happened before, right at that site. Luckily, it didn't happen there. Now, let's go on to the supply chain. So we talked about refinery situation, we talked about transport vessels, pipelines. Now let's talk about very large liquefied petroleum gas storage facilities like happen at a refinery or at the end of a pipeline that is transporting liquefied petroleum gas. This is an accident that happened in 1966 at an ELF facility in Faisin, France. This shows the event as it was unfolding. What are those? Those are fireballs. What's that? This was a BLEVE of one of the spheres. Now, I'm going to go into detail about how this happened and some of the reasons this happened. This happened at the bottom of the vessel. They would have to drain liquid out of the bottom of this sphere. So if you've got moisture in the gas that's going into this system and it condenses, where's it going to end up? It's going to end up at the bottom. So they had a system at the bottom for taking samples. They had a valve right on the bottom of the sphere. They had a 2-inch pipe coming out of that valve. They had a T with a line coming off of it and a little sampling valve, and then they had another valve at the bottom of this line. The procedure was, and this was in the written procedure and the training given to the operator, was that you were supposed to open the top valve nearest the vessel, not the bottom valve, and then open very slowly the side sampling valve to get water out before you took your sample of liquid propane. This was for quality testing. That's not what was done. It resulted in a major fire in BLEVE with 5 of the 8 LPG storage spheres, these huge spheres, being destroyed. 18 fatalities and 81 people were injured. Now, how was this system designed? And this is another example, like I said with Kingman, where standards were changed after this incident happened because of some lessons learned. So when you get very large quantities of liquid propane coming onto the ground in a confined area, it's not all going to evaporate, because what happens with a liquefied gas as it pours out goes to lower pressure? Expansion cooling. Joule-Thomson effect, it cools. And so you're going to have a very cool liquid, and it pools under there. And so how was it designed under those spheres? It didn't drain away. It pooled right under the sphere. The vapor, it started to evaporate. The vapor moved. It moved over to an adjacent roadway, found an ignition source, flashed back to the pool, and then you had a pool fire right under this huge sphere of propane. So then the firefighters came after these mistakes were made by the operator. The operator couldn't close the valve. He opened the bottom valve. An ice plug came out. He couldn't reclose the valve. He'd opened the top and the bottom valves. Didn't open the side valves. He was worried about using a nearby phone, turning on his truck to go to call in the accident. So it took him 10 minutes to report the event. I mean, he did the right thing. He didn't want to have an ignition source. But with this kind of situation, the sooner you find an ignition source, the better, typically. But anyway, after this scenario was playing out, the 90 minutes after the initial release began, the propane sphere ruptured. What did the local firefighters do? They came and started putting liquids on the adjacent vessels, not the vessel where the pool fire was. Lack of training. Remember when I put in that list of the key elements of a management system that's recommended by the American Institute of Chemical Engineers Center for Chemical Process Safety, one of the elements that is not in the OSHA PSM standard is stakeholder outreach. And what is one of the big stakeholder groups? Emergency responders, firefighters. They were not prepared to fight that fire, and they fought it in the wrong way. And unfortunately, a lot of them died because of it. This is what the scene looked like as the fire continued for several days. So what are the root causes? Lack of operator training. Maybe lack of operational discipline. Maybe he was trained adequately, but there was a poor process safety culture, and he said, it takes me too long to do it this way. I've done it this other way many times before. We've never had any problems. So I'm going to open both valves, get all this stuff out of here quickly instead of doing it according to procedure. Poor communication systems, a delayed emergency response, ineffective control of vehicular traffic. Once the release occurred, they should have shut down the roadway. Local fire brigade wasn't trained properly. Deficiencies in sampling system piping, lack of permanently installed water sprays, as well as the design of the system. They should have had the liquefied petroleum gas, if it did come out, drain away from the sphere. When I visited and was working at this liquefied natural gas facility, it was very interesting. A huge liquefied natural gas storage tank stored at atmospheric pressure under cryogenic conditions. I looked through the safety case studies, their scenarios. How did they design the system for a breach of containment? They had a series of collection dikes around the system that were very narrow, very deep, that flowed away from the vessel. So if they had a liquefied natural gas leak, it flowed into these channels that minimized the exposure to the air and drained the material away from the tank. So if they had a pool fire, it wouldn't impinge on the vessel. Standards have been changed, and now when you look at the design standards, they talk about drainage. A simple, passive, mitigative measure that could have prevented this catastrophe. Now, have we had any other serious accidents at very large LPG facilities? Unfortunately, yes. Near Mexico City, 1984, same type of facility. Terminal had 4 1,600 cubic meter spheres, 2 2,400 cubic meter spheres, and 48 horizontal tanks. 9 explosions occurred at this event. 600 people. 600, that's not a typographical error. 600 people died from this incident. 6,000 were injured, many seriously, serious burns. 200,000 people were evacuated. And how many of us remember this incident?
They have one in the lab.
There was another incident near the border, yeah, much less serious. $30 million in property damage. Sequence of events. What did they do wrong when they designed this? There may have been operator errors, but there were, again, like in the case of Fays in France, there were flaws in the design. They did not have gas sensing and automatic shutoff at this facility. So they had a rupture of a line. And they also didn't train people. They didn't go through scenarios. In other words, if you have a drop in feed line pressure, what's the reason for that? When you have a release of liquefied petroleum gas, like in the case in Italy, 90 seconds, it's all over. You have to respond quickly. They spent 5 or 10 minutes thinking about what to do when the line pressure dropped. When you have a flammable gas release, you have to have an automatic shutdown and shut off. It didn't happen. So the drifting cloud eventually found a source, and then it just went one container after another BLEVE'd at this facility. Terrible disaster. Total chaos. And most of those people, there are a lot of people the facility killed, but most of those people were people who lived in the area, and many horrible burns. As I mentioned, root causes related to original design, lack of design standards that were adequate. One of the key things related to, and one of the reasons I volunteer to come and teach courses like this, is to hopefully people won't forget these incidents, that we don't get complacent, because these kinds of incidents can happen in California if we don't follow the guidelines and standards and keep the controls in place. And that's one of the roles the folks in CUPA. And one of the things that I hope, what's the best discipline? It's not having CUPA go out and regulate and make people do things. Hopefully that the regulated community has the operating discipline to do this themselves because they understand the consequences. And the majority, many people understand, know these stories, and know what the potential consequences can be. Let's talk about smaller incidents, propane truck loading and cylinder filling terminals. How many of you have one of these facilities in your jurisdiction? I would be surprised if any of you do not. So if you don't know you have it, you probably do. It's somewhere in your jurisdiction. And can things go wrong at these facilities, and have they? These, again, are some of the listing of things I was mentioning, of things that can go wrong. And some of them have to do with mechanical integrity. And also following instructions. Let me go back. Operating procedures, conduct of operations. Conduct of operations is not in OSHA PSM. It's operating discipline to do what you say you're going to do. So what happened in Toronto, Canada in 2008 at one of these facilities? A young operator did a truck-to-truck transfer, absolutely forbidden. And this is what happened as an end result, in addition to him losing his life. Luckily, there were no other fatalities and no other serious injuries, but this was a major event. 12,000 residents were evacuated within a 1.6-mile radius of this facility. A 50 or 60,000 gallon bullet tank with propane in it is a big deal in terms of consequences, especially if it BLEVEs. Convenience stores. Restaurants in rural areas that have propane heating systems. This is an example that is almost beyond belief for me in terms of all the things that did not go right. There are industry groups. Remember I mentioned that there are various associations, the Propane Gas Association. The Propane Gas Association, in cooperation with an organization called the Propane Education and Research Council. It was put together, founded under an act of Congress. I went to take this course just to see what they offer and also get some of my continuing education units, and found it very interesting. Now, this is another Chemical Safety Board Action and Investigation report. And this one to me is just startling, what went on. So I'm going to show you part of the video. Is way too long, but I'm going to show you part of it so you can just get a little bit of the flavor of what went on.
At 10:53 a.m. on January 30th, 2007, a propane gas explosion destroyed the Little General convenience store in rural Ghent, West Virginia, near the city of Beckley. The blast killed 2 propane service technicians and 2 emergency responders from the Ghent Fire Department. A volunteer firefighter was seriously injured, as were 4 store employees who were inside the store when the gas ignited. West Virginia State Fire Marshal Sterling Lewis recalls the day of the accident.
It was a scene that was horrific to me because of the familiarity that I had with the area growing up there for 52 years. There was a tremendous amount of carnage. We had firefighters down. We had civilians that were down.
I believe the main reason that we investigated this accident was that there was a tragic, unnecessary loss of life.
In this case, we had 2 emergency responders that were killed and 2 propane technicians in a seemingly routine operation. And from that standpoint, the CSB thought it was important to uncover the root causes and find out why these people died.
Nearly 30 minutes elapsed between the release and the explosion. If there'd been an evacuation during those 30 minutes, all of the lives would have been saved.
The Little General gas station and convenience store was located on Flat Top Road in Ghent. Inside the wood-framed building, the store sold soft drinks, magazines, and snacks, as well as pizza, which was cooked in 2 propane-fired ovens. In 1994, the Southern Sun Company installed a 500-gallon propane tank against the back wall of the store. Southern Sun sold its propane business to Feral Gas in 1996. The logo on the tank was changed, but the tank itself was left in place. Years later, in January 2007, the Little General Company changed propane providers from Feral Gas to Thompson Gas. Appalachian Heating, a local firm selling propane for Thompson Gas, installed a new tank 10 feet from the building. There were still about 350 gallons of propane in the old tank, which Appalachian Heating intended to transfer through a special valve, hose, and pump to the newly installed Thompson gas tank. To make such a transfer, a technician must first unscrew a safety plug from the top of the liquid withdrawal valve on the tank to be emptied. The safety plug has a small hole in its side called a telltale. If propane is released through the hole, it is a warning that a dangerous release is likely if the plug is completely removed. So if propane is seen, the plug should be retightened. If no propane is observed escaping, the plug may be removed, and a valve with a special fitting is then threaded into the liquid withdrawal valve. This special fitting depresses a spring-loaded mechanism, allowing propane to flow through the valve and into the hose to transfer the propane. The CSB determined that on the day of the accident, several factors combined to turn what should have been a routine tank exchange into a tragedy. On the morning of January 30th, 2007, 2 technicians from Appalachian Heating arrived to put the new tank into service. The lead technician then departed for another job site, leaving an inexperienced junior technician to prepare for the transfer of propane unsupervised. At about 10:25 a.m., the junior technician began to unscrew the safety plug from the liquid withdrawal valve, a valve the CSB would later determine was permanently stuck in the open position. Propane likely flowed out of the hole in the plug, but the technician had not been trained on the importance of checking for the escaping gas. Immediately, as the technician removed the plug, a jet of propane sprayed upward through the valve. A billowing white cloud of flammable propane vapor formed behind the store. The propane struck the eaves of the building and flowed into the store through vents in the roof overhang and directly into the restrooms through 2 vent pipes. The flammable gas also diffused down through the ceiling. The gas, colored gray here for illustration, was invisible to the employees inside, but they noted the spreading odor associated with propane. The dense vapor also accumulated at ground level around the tank and the foundation of the building. The technician, standing in the midst of the propane cloud, was unable to stop the release due to the force of the jet. Over the next almost half hour, all 4 store employees remained inside, and the technicians stayed by the tank as others responding to the propane release arrived. There was no evacuation as propane continued to escape from the tank. At 10:28 a.m., shortly after the leak began.
So what I wanted to talk about is this. When you look at process safety and managing risks, what's exempt under the requirements under regulations? Propane used for commercial or retail fuel, right? Fuel use for cooking or heating. We went through those items: compliance with standards, operating discipline. They mentioned why was that facility, that tank had been right next to the wall. The standard says minimum 10 feet away from the wall. They had done inspection after inspection. None of the inspections pointed out that this tank had been improperly installed and it was too close to the building. If it hadn't been that close to the building, the vapors may not have gone inside. The basic course that's offered by Propane Education and Research Council to all employees for a propane distributor, basic principles and practices of propane. I went and took the course and I passed the test. Responding to events with loss of containment. They don't call it loss of containment, they say leaks. If there is reported gas odor inside a building, instruct the customer to leave the area immediately. Shut off the gas if it's possible. Report the leak. Do not return to the building or the area until your propane retailer determines that it's safe to do so. The first instructions. The next course that's given, this is a day-and-a-half course they have to go through. And they're taught about the NFPA standards for internal gas piping and external for propane systems. So, lack of training. That operator who was technician was left out there was clueless as to what should be done. He didn't understand the meaning of that telltale when you started getting propane out. He should have immediately closed it. He didn't know how to mitigate the situation. Obviously, many before him had inspected and they had installed the tank in the wrong location. And then the fire captain, when they came, didn't immediately order an evacuation. So this was just a disaster. Now, unfortunately, the bad news continues. Shortly before this one, there was an incident in Milwaukee. So when the CSB was investigating, they reported an incident in an industrial facility where the people should have been better trained. So employees at the site discovered a pool of liquid propane near a propane pipeline that they were using for on-site fuel. Most employees began evacuating. 3 remained to attempt to repair the leak. You hear about this all the time, where people remain behind and don't evacuate and try to do something. PVC plant in Illinois. about 2005, I think it was. They had an unintentional release of vinyl chloride vapors. 2 or 3 people were killed immediately. 1 or 2 other died later because they didn't evacuate. Once you have a flammable release liquefied gas, get out of the area. So anyway, there's another example. The news continues to be bad. Albert City, Alabama, 1998. On-farm use. This one was on a turkey farm. This was for 18,000 gallons. Now this is another interesting example. I'm going to show a video, again a CSB video of this incident.
April 9th, 1998, the Herrig Brothers Poultry Farm, Albert City, Iowa. 2 teenagers were joyriding on an ATV when they crashed into piping from a 42-foot-long propane storage tank. Propane gushed from the tank. An excess flow valve failed to stop the leak. The gas likely drifted toward a hot propane vaporizer 37 feet away and ignited. Flames engulfed the tank and began to heat the propane inside. 20 volunteer firefighters were called to the scene, but were unable to stop the leak. They planned to let the fire burn itself out. But meanwhile, they would spray down the adjacent turkey barns to keep the fire from spreading. Based on their training and guidance, the firefighters believed that in the event of an explosion, they would be protected if they stayed away from the ends of the burning tank. As the fire continued to rage, flames directly heated the upper section of the tank wall, above the level of the liquid. Without liquid to transfer the heat, the upper section of the tank wall began to overheat and weaken. Minutes later, the propane tank blew apart, sending metal fragments in all directions. Pieces of the tank struck the firefighters, killing 2. Other deadly fragments narrowly missed 2 others. 7 firefighters were injured. Other debris smashed into buildings. The firefighters were victims of a BLEVE, a boiling liquid expanding vapor explosion, a hazard they had never trained or prepared for.
This accident resulted from a lack of effective training materials for firefighters, as well as a lack of understanding of propane BLEVE hazards. If the firefighters had just kept a safe distance away from the burning tank, no one would have been harmed. And that's really the tragedy of this case.
Chemical Safety Board investigations have revealed that many communities, companies, and responders need to be more knowledgeable and better prepared.
Ghent, West Virginia. 2 emergency responders and 2 technicians are killed.
Hopefully, you know, we're going to learn these lessons one of these days, and there were a lot of problems with the way this system. Now, this system was in a rural area. It was on a farm, and the tank's located right there. And there was a line coming out from the bottom of the tank going to the vaporizer. And in a design according to standards, you would have stanchions around there so that you cannot drive a vehicle up near any piping around the vessel. Now this was in a rural area. They probably figured, well, we don't really need that. And so they didn't comply with standards. And this, of course, is the situation here where the firefighters were totally unprepared. If they were going to direct water onto the, it was fine to put a hose on the buildings. They should have done it with they should have put a hose up, had it sitting there, and then retreated and let the hose spray on the building, and also have a hose on the tank, on the top of the tank. May not have done any good, but at least they were going to be a lot farther back. But they shouldn't have been anywhere near there holding that hose. Now, there are a lot of fire safety standards that specify how these systems are supposed to be installed. Interior piping, it's NFPA 58 or 59? 58. And for the exterior piping, it's 59. And then there's a manual that provides a lot of guidance. So there's a lot of information out there, but people have got to have the competency. They have to understand the information and then know how to use it. And that, again, when you look at a lot of these other elements, stakeholder outreach, process safety, competency, compliance with standards, conduct of operations, operational discipline. And then, in the case of the store, again, that incident, measures and metrics and management review. They had all of these inspections. The CSB found inspection reports where they were checked off. Yes, the tank was more than 10 feet from the building, but for years, it was right there. Somebody was just going through and checking the box. I'm sure none of you have ever seen that happen before. But it can have tragic consequences when that kind of thing is done. So, hopefully some of you will come back for some more discussion of liquefied gases after lunch, and we're going to talk about some ways to do it right and some bad news about chlorine too. So, look forward to seeing you later.